Hi everyone, welcome back. You are watching the 13th lecture of EE635 Applied Linear Algebra. This would be the second module. So in the first module, what we have seen is that using this ancient result, Aryabhatta-Bezu identity, we can see that if we have minimal polynomial mu s, which admits a co-prime factorization mu equals pq, where p and q are two co-prime polynomials, then kernel pa, kernel qa, these two are two invariant subspaces, A invariant subspaces, whose direct sum is the whole space, right? So therefore, if we take a basis for kernel PA, say B1, and kernel QA, say B2, and take the union of B1 and B2, then that gives us a basis for the whole space. And in this basis, the linear operator A is represented by a block diagonal matrix, A11, 0, 0, A22. Right? That is what we have seen. Now the question is, can't we proceed any further? Can't we write this whole, this block diagonal matrix? Can it be written? Do we have to stop at only two blocks, or can we go even further? Right? That is what we'll see in this module. All right. So let me share my screen. Okay, here it is. So what we're going to do is we're going to look at this block diagonal representation in a little more detail. So what have we got here? We have A, the linear operator, represented in this basis B, is given by A11, 0, 0, A22, right? We have seen earlier that this A11 is actually nothing but A restricted to the subspace W1, because it's an invariant subspace. We can do this restriction. This is represented in the basis B1. Similarly, A22 is nothing but A restricted to the invariant subspace W2, represented in the basis B2. Right? Now, so these two are matrices. As we have seen, this is in K1 cross K1. This is in K2 cross K2, where of course K1 is dimension of kernel of PA, and K2 of course is dimension of kernel of QA. Yeah, that's what we have seen. Okay. Now, because this guy is a matrix, let's say mu1s be the minimal polynomial of A11, the minimal polynomial of A11, which is also to say that this is the minimal polynomial of the operator A restricted to W1, right? Similarly, say mu2, so we are defining it, let mu2s in Fs is the minimal polynomial of A22, A restricted to W2, right? Okay. Now what can we say about these minimal polynomials mu1s and mu2s, right? What we will see actually is the following, that this mu2s, so this is the claim, this is the lemma. We'll see a proof of this lemma very soon. So the lemma says that this mu1s is nothing but the factor ps of the minimal polynomial of the whole space, and similarly mu2s is nothing but the polynomial qs, right? So not only do we have a block diagonalization of our original operator A, but we have these blocks are such that minimal polynomial of this guy is PS and minimal polynomial of this guy is QS. Remember, this part corresponds to the subspace kernel PA. This part corresponds to the kernel, subspace kernel QA. Yeah, and accordingly, their minimal polynomials also match with these two factors P and Q. Surprising, right? Why shouldn't be? So let us try and demystify why should this be? Why is this true? Okay. All right. So now, so for that, what we'll have to do is we'll have to pay attention to the details of how we obtain this, invariant subspace decomposition. Okay. So we postpone the proof. The proof will emerge naturally. That's what my belief is. Let's see. So, okay. So first, notice the following. So say this basis B1 that we had for W1, suppose it's given by W1, W2, dot up to WK, these WK1, these K1 vectors. Similarly, suppose B2 is given by W, what should I write? K1 plus 1, WK1 plus 2, dot up to WK1 plus K2. Of course, that is the same as N. Yeah, is that all right? Now, when I have done this, remember this was my vector space V, and V gets identified with f to the n, where every vector V gets mapped to its representation in the basis V. Now notice under this representation, W1's representation in V goes to, of course, E1, because that's the first basis vector. What is B? B is nothing but B1 union B2. This is an ordered basis which starts with W1 and going via WK ends at WK1, ends at WK1 plus 1, ends at WN. This is the basis. So if I express the first basis vector in terms of this basis, I get 1 and all zeros. That's what I've written. And of course, this trend will continue till WK1, which of course would be given by EK1. And then WK1 plus 1. This is where the new the other subspace W2 starts, right? And then finally Wn must be nothing but En. This is the representation, right? And of course, if I have A, the operator, its action on W1 when represented in this new basis is nothing but representation of A in this basis B into W1 in this representation, isn't it? And this is true for all W, in fact. Right. Yeah, this is true for, in fact, all the vectors where I goes from 1 up to n, right? And so therefore, this is nothing but A, B, EI, where EI is the ith basis vector. I hope so far it's clear. You can notice easily that this also implies, from here it follows that if I have any polynomial fs, right, then if A is an operator, its action on Wi, the ith basis vector represented in this basis, is nothing but if A's matrix representation in the basis into EI. Okay, let's not do any step jumps. Let's just write everything that we know. This is Wi's representation in B, which is the same as if A, B, EI. Right? Now this goes to you as a homework. In fact, it's an immediate attention problem. Show that f A's representation B is nothing but f of A's representation in B. Right? Do this. It's very simple. Just need some working out, and that's it. Yeah. All right. Now, if this is the situation, so provided you do this homework problem, you'll realize that this is nothing but if this matrix into EI. Okay, right? Now, all right. So now notice the following. So first thing that we notice from this expression is the following. For all I going from 1 to up to K1, if I take PA and make PA act on WI and look at its representation, what am I supposed to get? My formula tells me that this should be P A B, right? EI. Yeah. What is this? Because A is block diagonal, this is nothing but P A11 0 0 P A22 EI. And remember, this size is K1, this size is K1, this size is K2, this size is K2. But WI is what? WI is the ith basis vector in, right? This is in B. So for I1 up to K1, these vectors are in fact in B1, and therefore these vectors are in fact in W1, which happens to be kernel of PA. Yeah, if that is so, then this implies WI belongs to kernel of PA for all I going from 1 to K1. So therefore, this expression that I have here, this is a zero vector. This is the zero vector. So its representation must also be the zero n tuple, right? So then what have we noticed? What we have noticed is, so therefore, this matrix PA11 0 0 PA22, this into EI is equal to 0 for all I going from 1 to dot 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 up to K1, which means this matrix that we have here, the first K columns of this matrix are 0. The first K1 columns of this are all zeros, right? But this is a K1 cross K1 matrix. So the first K1 columns being 0 means this matrix, the square matrix must be 0. This means PA11 must be the 0 matrix, right? So you see, as far as this matrix A11 is concerned, A11 is such that PS is an annihilating polynomial. Yeah, but mu1 is the minimal polynomial, so mu1 is the generator of the annihilating ideal, which means every annihilating polynomial must be a multiple of mu1. So therefore this implies P belongs to the ideal generated by mu1, which of course implies mu1 divides P. Yeah, is that all right? But that's not all. What we would show actually is that P will also divide mu1. But for that, we have to go via this calculation. Similarly, following exactly the same steps, but for A22, we can show that Q A22 must be equal to 0. This goes to you as a homework. If Q A22 is 0, then this would imply that mu2 would divide Q, right? Okay. Now, here comes the interesting part. Suppose I just look at PA, right? Now PA's representation by our homework is nothing but PAB, yeah, right? Which is the same as PA1100 PA22. Okay. Now, in fact, I don't need P. This is true for all polynomials. Yeah. So let me just insist on that. Let me write this down for general polynomial. Yeah. Right. So in particular, if I now look at mu1 A B, this is going to be mu1 A11 0 0 mu1 A22. But mu1 happens to be the minimal polynomial of A11, so this must be 0. So therefore, this is the same as saying 0 0 0 mu1 A22. Yeah, is that all right? Similarly, now let us notice that QA, its representation B, is nothing but QA11 0 0 and following our so Q, right, QA22. Yeah, but you see, following your homework, QA22 is 0. QA22 being 0 would mean this is QA11 0 0 0. So therefore, if I now look at this polynomial mu1 A into QA, right? Look at this representation. This certainly would be mu1 A representation in B, QA representation in B, but mu1 A we know is 0 0 0 mu1 A22, and this is QA11 0 0 0, where this size is Q1 by Q1, this is Q1 by Q1, this is K2 by K2, this is K2 by K2. So this product is commensurate, and if you do the product, you get 0 0 0 0. K1 K1 K2 K2. So what does this mean? This is the zero matrix, which means this must be the zero operator. So therefore, mu1s QS is an annihilating polynomial of the operator A, which then means that mu1 Q must belong to the ideal generated by mu, yeah, right? Because mu is the polynomial, is the minimal polynomial of A, which is the generator, the monic generator of the ideal of annihilating polynomials. So therefore, mu must divide mu1 Q. But you see, mu is actually product of PQ, must divide mu1 Q. Of course, this means P must divide mu1, right? So now, because P and Q, mu, all of the P, mu1 both are monic by definition, because this is a factor of a monic polynomial. So this is monic. I mean, you can make this monic, P and Q both monic. Mu1 being minimal polynomial by definition is monic. So this implies, so earlier we had proven that mu1 divides P, you see, mu1 divides P, and now we have proven that P divides mu1, which means P must be equal to mu1. And similarly, therefore, Q must be equal to mu2, right? So now, so what have we got out of this? It means that not only is this V decomposed into a direct sum decomposition of W1 and W2, this A's representation in this basis actually is such that this is A11 restricted to W1, this is A22 restricted to W2, and its minimal polynomial is this one, is PA. So what we can conclude here is that W1 defined as kernel of PA. Not only that, A restricted to W1 has minimal polynomial PA, right? W2 defined as the kernel of QA must also have A restricted to W2 has minimal polynomial QA, right? This sort of apparently innocuous kind of result actually has grave repercussions. How so? Well, here is the thing. Notice, what did we do? We had V, we decomposed it into W1 and W2. But then when I restrict my operator in W1, I get a smaller operator, right? Because W1 of course is smaller dimensional subspace, so it's A restricted to it. It's everything is smaller dimensional. Yeah, A11 is K1 by K1. Now this matrix or this operator, that is A restricted to this W1. So if I restrict myself to this some smaller dimensional subspace, here I have the operator restricted to it, and its minimal polynomial is that factor. So now if I look at that factor and factorize this factor further into two co-prime polynomials, two co-prime factors, I can further decompose W1, yeah, as a direct sum decomposition of A restricted to W1 invariant subspaces. So here W1, W2 were invariant subspaces. Now I can have further invariant subspaces contained in them. So W1 as well as W2 can be broken up into such two pieces. Those pieces can further be broken up, which would correspond to further co-prime factorization of those polynomials, right? So in the end, what we get is the following. So by repeated application of the co-prime lemma, what we'll get is, so thus making use of this observation, together with the co-prime lemma, we get the following. What? We get the following theorem. Yeah. So A linear operator from V to itself. V is a vector space over F. Dimension of V is equal to n less than infinity. Mu S is the minimal polynomial of A. Let mu be factorized into co-prime. Now, what do I mean by co-prime here? Pairwise co-prime. So factorize as mu equals P1, P2 dot 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 up to PR, right? So this means GCD of PI Pj is equal to 1 for all ij. I of course not equal to j. This is what we mean by co-prime. It is like pairwise co-prime. So pairwise co-prime factors P1 up to PR like this define define Wi to be kernel of Pi. Okay, let Bi be a basis for Wi, then A's representation in this space. Oh, okay. Wi define B union I going from 1 to R, Bi, then B is a basis for the whole space V, and A's representation in this basis is going to be A11 dot 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 up to ARR. All these are block zeros. AII is a matrix of size FKI cross KI, where KI is equal to dimension of Wi, and minimal polynomial of AII is Pi. That's the theorem. Quite a mouthful, but I hope you understand what's going on. So let me repeat. What we have a vector space V, we have an operator A, V is finite dimensional, defined over the scalars are coming from the field F, right? So now I look at the minimal polynomial of A. I find out some polynomial. I factorize into pairwise co-prime factors as many factors as I can. Yeah. So this is like, this reminds us of prime factorization of positive numbers, positive integers. Positive integers can be factorized into prime powers, right? Where primes are these, the prime powers that I'm writing, they're distinct. So that's what I mean. So when we have distinct primes, that means they're co-prime, mutually co-prime, pairwise co-prime, right? So here what we'll do instead, we have this polynomial. We'll look at this irreducible or prime factors, prime powers. Yeah. So that polynomial can be broken up into product of such prime powers, such irreducible polynomials powers, such that those irreducible polynomials and their powers, they are mutually co-prime, right? Pairwise co-prime. And then we're going to look at the kernel of these factors, of these co-prime factors, right? Those kernels, by virtue of being kernels of polynomials of the operator, will be A invariant. Yeah, because they're pairwise co-prime, their direct sum will be the whole space. Because they're invariant and they give us a direct sum decomposition of the whole space, A represented under a basis coming from these this direct sum decomposition would be a block diagonal matrix, where each block would correspond to one of those co-prime factors. Yeah, let us see a consequence of that, and then it will be easier for us to understand. Yeah, a corollary first of this fact is that if mu, that is the minimal polynomial of A, is given by s minus lambda 1 dot 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 up to s minus lambda r, where lambda I is not equal to lambda j for I not equal to j. That means these are all linear factors. So because lambda 1 and this lambda I and lambda j are distinct, that means these are co-prime factors. If minimal polynomial is like this, then the whole space V gets factorized into direct sum I going from 1 to R. Direct sum of what? Direct sum of kernel A minus lambda I into identity. Right? What are these? Any vector in this kernel is an eigenvector, which means V can be written as a linear combination. V admits a basis involving only eigenvectors, right? Which means Earlier we had seen that this means A is diagonalizable. So you see, if the minimal polynomial is this, so is a factor, is a product of linear factors, right? Each having degree 1, and these are distinct coprime, right? So lambda i's are distinct, so these factors s minus lambda I are coprime, right? So if the minimal polynomial admits a factorization like this, then the matrix is diagonalizable. On the other hand, if the matrix is, or the operator is diagonalizable, then its minimal polynomial is of this form. So this in fact is an if and only if condition. Okay, earlier we had seen that algebraic multiplicity must be equal to geometric multiplicity is necessary and sufficient for diagonalizability. Here is another equivalent condition added to that. Okay, further, let us look at this other corollary. Suppose we are in a vector space over C. V is defined over the scalars which are coming from the complex number. So it's a complex vector space, if you like. Everything else remains the same. It's finite dimensional. A is an operator from V to itself, and so on. In that situation, mu, the minimal polynomial of A, would be factorizable as s minus lambda 1 to the power k1, s minus lambda 2 to the power k2, and so on. This is the fundamental theorem of algebra. This is by the fundamental theorem, capital T, yeah, because this is a name, fundamental theorem of algebra. I hope you know that. Fundamental theorem of algebra says that every polynomial over complex numbers factorize into linear factors. That is, they have their roots. All the roots are there over the complex numbers. We don't have to search for roots outside. Over real numbers, this is not true. Over real numbers, there are quadratic polynomials whose roots may not be reals, as you've already seen many times. Yeah, it depends on the discriminant of the quadratic polynomial, b square minus 4ac, right? Over complex numbers, that's not the case. Every polynomial will factorize. So every polynomial will factorize like this, right? So if the polynomial factorizes like this, then I can define my subspaces Wi's as kernel of, by the way, this are such that lambda I is not equal to lambda j. This is very important. Yeah, they have to be distinct. So s minus, sorry, not s, a minus lambda I into identity. So these are the kernels. These are my A invariant subspaces. Lambda I to the power ki. Yeah. These are the factors. These are the coprime factors. See, if there is a factor, say s minus lambda square, right? Then s minus lambda is a factor. I cannot take kernel s minus lambda once and then once again kernel s minus lambda. So I have to club all the factors with the same root together. That's why I'm writing s minus lambda I to the power ki. Lambda I, lambda j would be distinct. All right. So these are coprime factors. Therefore, my V must be W1 direct sum W2 direct sum dot 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 direct sum W. How many were there? WR. Okay. And in this basis, so B1 would be a basis for W1 and so on. BR. B, of course, then gets defined as union igram from 1 to 1. Bi is a basis for V, of course, because of the direct sum decomposition. And in this basis, A's representation is given by A11 going up to ARR. And of course, AII has minimal polynomial. What is it? What does it say? S minus lambda I whole to the power ki. That's it. This is the direct sum decomposition. So block diagonalization, direct sum decomposition. Can anyone tell me what would be the size of AII? AII belongs to, oh, sorry, this is C, huh? So all complex numbers. C size would be Ki cross Ki. Yeah, because this space has dimension equal to Ki. So that goes to you as a homework. Prove that. Yeah. Prove that dimension Wi is equal to, does it have to be Ki? No, my bad. It doesn't have to be Ki. Sorry. My bad. No, this is not a part of the theorem. This is not required. Yeah, this is not true, in fact. Yeah. Sorry, my bad. Okay, yeah, but this much is fine. Okay. Now the next step that we're going to see, that would be in the third and final module of this lecture, is that, so then because I can now have decomposed the whole operator into this block matrices where each block has its minimal polynomial given by s minus lambda I to the power ki. This means what? This means if I want to go even further than this, I need to analyze this situation. So it now remains to investigate the following situation. What is that? V A is a linear operator from V to itself. Yeah, V is over this field of complex numbers. Dimension of V is equal to n finite, and minimal polynomial of A mu s is given by s minus lambda to the power k. Yeah, this is the situation. So this is like each block is of this kind, isn't it? Right, each block is of this kind. So this number k, of course, yeah, is some number. We'll see what is the meaning of this guy. Now the question is, in this situation, can we have, in some sense, some nice representation of A? Can I find a basis for V in which A would look something nice? Yeah, we'll see that A will admit a representation by what is known as a Jordan canonical form, a Jordan block. Yeah, A would admit various different Jordan blocks. Okay, the highest of which would have size K, but there could be multiple such, right? Multiple such Jordan blocks. Okay, so once we do that, then we'll know that once we have done this block diagonalization using the direct sum decomposition, the next step would be to look at each of these blocks and obtain these Jordan blocks. So each block, that is A11, A2, A22 up to ARR, each of those blocks can further be broken down into these Jordan blocks, right? What do we mean by Jordan blocks? How to obtain them is what we'll discuss in the third and final module of this lecture. Okay, so see you then.